Today we are going to discuss the topic which is a thought behind heuristic searches. At the end of the session, you will be able to demonstrate various heuristic search algorithms which encounter having done with the drawbacks which were there in uninformed searches. A heuristic function is a function that estimates the merits of each node that we generate. Any approach to problem solving that uses a practical method or various shortcuts in order to produce solution that may be optimal but are sufficient behind a limited time frame or deadline. Therefore, we are going by values to direct our particular path from the start to the goal. A heuristic function estimates how close a state is to the goal. It calculates the cost of an optimal path between the pair of states, and the value of the heuristic function is always positive, which tells us we have to go ahead in a particular direction, and we have a number of algorithms like best first search, hill climbing, beam search and tabu search, which are based on heuristic techniques in order to find out the best nodes that lead us from the start to the goal. In the best first search algorithm, we have a traversal technique that decides which node is to be visited next by checking which node is the most promising one, and then we check for it. For this, it uses an evaluation function to decide the traversal. The cost of the nodes is stored in a priority queue. Here we are not using a simple queue or we are not using a stack, but we are using a priority queue for its implementation. This makes the implementation of best first search the same as that of breadth first search, which used a queue. We will use the priority queue just like we use a queue for the breadth first search. However, the priority tells us about the best of the nodes that are at a particular level. The rules to be followed are: create a priority queue, which is called as PQ. The rule 2, insert the start in the PQ, that is the start node. So PQ is inserted. Then the rule 3 is to delete all elements of the priority queue one by one. Following the rules, if the element is a goal, exit, else traverse the neighbors and mark the node as examined. And rule 4 is to end your procedure. Therefore, this algorithm will traverse the shortest path first in the queue, and the worst case scenario is that the algorithm will take O of n into log n time, where n is the number of nodes in your particular graph, which is your search graph. The next method is hill climbing. This is a local search algorithm that continuously moves in the direction of increasing elevation. So values are associated with it to find the peak of the mountain or the best solution to the problem. It terminates when it reaches a peak value where no neighbor has a higher value. It is also called a greedy local search, and it only looks to its good intermediate neighbor state and not beyond that. A node of hill climbing algorithm has two components, that are a state and a value. So we are going by values associated with a particular node, and therefore we call them as heuristic. So hill climbing is mostly used when a good heuristic is available in our particular scenario. So the algorithm is to evaluate the initial state. If the goal state, if it is a goal state, then return success and stop. Otherwise, go to step 2, loop until a solution is found and there is no new operator left to apply. In the step 3, we select and apply an operator to the current state, and in step 4, we check for the new state. If this new state is the goal state, return a success and quit. Else, if it is better than the current state, then assign the new state as the current state. Else, if it is no better than the current state, then return to the step 2. Otherwise, exit your particular algorithm. The next algorithm that we have into consideration is beam search. In hill climbing, we may encounter too many nodes, and therefore we have to restrict these nodes by pruning them. And therefore we use a beam which has a width associated with it and a branching factor for a particular node where decision has to be taken. So a heuristic search algorithm examines a graph by extending the most promising node. It always expands the W number of the best nodes, where W is the width. At each level, it progresses level by level and moves downwards only from the best W nodes at each level. So it is following a depth first search with the width restriction associated with it. It uses breadth first search to build its search tree. At each level, it only evaluates W number of states. Each node are not taken into the account, and the heuristic cost associated with the node is used to choose the best nodes, and the width of the beam search is denoted by W, and B is the branching factor at every depth. There will be always W into B nodes under consideration. So the beam width bounds the amount of memory needed to complete the search, but it comes at a cost of completeness and optimality associated with your solution. The algorithm has an input to be start and goal states, local variables, an open list, node, successors, W open and found, and the output to be yes or no. That is, if the search is successfully done, yes, and we start the algorithm by taking the inputs, we associate the node root value, okay, if it is found to be false. If the node is a goal node, then we return a particular success, that's where it is true. Else, if success of a node, if any, when the estimate cost, and we store this in an open list, which is a list of visited nodes. While found is false and not able to proceed further, we go for sorting this open list, select from the W elements that the width, which are in the width of your particular beam from open list, and put it in the W open and empty the open list. For each node from this W open list, which are the nodes in the width of your particular beam, if the node is a goal, then we are done. Else, find its successor node. If it is an estimate better, then put it in the open list. If it is found, then we say it is true, then we return yes and we are done. Else, return no and stop the algorithm. The next algorithm is a little bit deferred, which is the Tabu search. This is a commonly used meta-heuristic algorithm for optimizing the model parameters. As we know, a meta-heuristic algorithm is general strategy that is used to guide and control the actual heuristics. It is often regarded as integrating the memory structure and the local search strategies, thus saving memory. As the local search has a lot amount of limitations, Tabu search is designed to combat a lot of these issues. So the basic idea of Tabu search is to penalize the moves to take a solution into previously visited and search spaces, and these search spaces are called as Tabu. Tabu search, however, does deterministically accept non-improving solutions in order to prevent getting stuck in a local minimums but going ahead to get your particular solutions. Therefore, a Tabu search that concentrates on the issue of the search spaces visiting and getting the solution from it is our question of concern. We start with the initial solution. This can be any solution that fits in the criteria for an acceptable solution. We generate the set of neighboring solutions to the current solution to check whether it is better, and we label such a solution as n of s. We choose the best solution of n of s and label the next solution as s dash. If the solution s dash is better than the current solution, update the current solution to be the best, and we update this tabu list by improving all the moves that are expired already past the tabu tenure and add the new moves s dash to the tabu list. So the tabu list is always updated with latest nodes. Additionally, update of these solutions that fit an aspiring criteria, which we call as A of S. And if the termination criteria are met, then the search stops or it will move on to the next iteration. For our references, we have used. Thank you.